Hello everyone, welcome to today's case study on rotary wing unmanned aerial systems. This day is divided in two parts. First, we're going to talk about the applications and control theory, and in the second part we're going to be talking about perception and planning for MAVs. So in last week's lecture you already went through the first 3 points of the slide. You looked at how to model the aerodynamics of propellers and also how to model the system dynamics of MAVs and also how to design a simple Euler angle-based controller of a quadrotor. And today we're going to look at more advanced types of multirotors, at the applications, like what we can use them for, and then also we're going to look at another example of a more accurate controller, which is called the geometric controller for multirotors. So let's start with looking at different multirotor configurations, like any kind of multirotors that are different from the standard quadrotor that you already saw in last week's lecture. On the left side, you can see a simple extension of the quadrotor that you already saw, which is for once the hexacopter in the top image and an octocopter in the bottom left image. And the only difference to the standard quadrotor is that we add 2 or respectively 4 more propellers to the system. So this basically makes the system more redundant. We can still have 1 or 2 propellers failing while still having at least 4 propellers in the system to keep the system in hover. Otherwise, the control is very similar to the standard quadrotor, only the allocation matrix changes slightly. On the right side, we have a different propeller type, which is called the variable pitch propeller, which means that we can change the thrust not only by changing the rotor speed, but also by changing the pitch of the propeller, which is what we see here. So this basically makes the system more responsive, but also a lot more complicated to control and also mechanically more complex. So this is why it's really rare to use in MAVs. Another 2 types of multi-rotor configurations are the tail sitter and the tilt rotor that we see on the slide here. And the tail sitter, as an example, provides a vertical takeoff and landing. So that means that we can lift off vertically like a MAV, and then just in the air change the attitude to fly horizontally and use the wings in order to fly for longer time and longer distances, which is then obviously more energy efficient and you can cover more distance in large areas even though you can land vertically. On the right side we have a tilt rotor, which is special in the sense that we can rotate the arms and by that change the thrust direction of all the propellers with respect to the body. And that allows us to, for example, hover in any desired attitude that we would like. In that case, the control is again similar to the standard hexacopter, but we also have to account for the rotating arms, which basically changes the allocation matrix all the time. So let's look at a couple of classical applications on where we can use multirotors today. One classical example for the use of multirotors is in surveillance. So as we see here in this video, we can use multirotors after, for example, earthquakes to quickly create maps and to prepare and help rescue teams that can then go into these damaged areas to faster find their way around. So in that sense, with drones, we have easy and access to difficult or dangerous terrain. And we can also, of course, attach different kinds of sensors, like for example, also heat cameras to find buried people in these damaged areas and help rescue teams find them faster. Another example we can see here in this video, which is basically a delivery of small lightweight objects with drones over not too long distances. So just as an example, this has already been used by the Swiss Post a few years ago to transport laboratory samples over the Lake of Zurich. But obviously, due to the battery, it's limited in its flight time and also in its distance. Something else that also has come up over the last years with drones is to use them in light art. So basically, this is mostly what Intel is doing, is that they use hundreds to sometimes even thousands of drones at the same time to synchronize their flight and light when they are in the air to create some images synchronized to music, for example. So all these previous examples have focused on free flight of drones, so without being in contact with their surroundings. And in more recent applications, we've also started to use drones for interaction tasks, so that they actually need to touch or be in contact, in physical contact with their environment. And this, as we can see here in this video as an example, can then be used for industrial inspection. So for example, we can use sensors to map the thickness of metal tanks as an example. Other applications that involve interaction with the environment can then, for example, be used to inspect concrete or also to clean surfaces or also to paint surfaces, as we see in these video examples here. So now, having seen some examples of multirotors and their applications, we want to have a look on how we can make them autonomous. So what does it mean for an MAV to be autonomous? So we basically have the definition of autonomy here on the slide, which says that an autonomous robot is an intelligent machine able to perform tasks without explicit human intervention. So, and we see here in this diagram the four basic components for this autonomy, which is on the left side, first of all, the planning, then the control, then this control is fed into the robot itself, so into the MAV, and then we need some perception, which is then actually again used in the later planning step. So again, the planning generates a path for the robot to execute some mission that's defined by the user. The controller computes the controller commands to make the MAV follow the desired trajectory. The MAV executes this dynamics, and the perception is then estimating all the new states. And depending on what sensors we use, it uses the environment to estimate its current state. And in this part of the case study, we're going to now look at the control module that's responsible for the stability and the trajectory tracking. And in the second part, Michael is then going to look into the perception part. In the lecture from last week, you already learned about a simple controller that controls the attitude and the position of an MAV based on the Euler angles. So in this case study now, we're going to look at a different, a little bit more sophisticated controller, which is called the geometric controller. And this also controls the attitude and the position, but in a more correct way. First of all, we're going to look at the dynamics of a multirotor and how we can model them from physical principles. So here on the top, we can see the translational dynamics for position and velocity. And on the bottom, we have the rotational dynamics. So the time derivative of the attitude, which is represented by the rotation matrix from the body to the inertial frame, and the time derivative of the angular velocity, which is on the very bottom. And we can also already see from these equations here that the translational and the rotational dynamics are actually coupled. And we can see this because RIB, so this rotation matrix, appears in the translational dynamics, but also in the rotational dynamics. What we also see in those vehicle dynamics are these virtual inputs U1, U2, U3, and U4. And so what are those? So basically, U1 is the total thrust, so the sum of all the rotor speed squared with the thrust coefficient. So basically, this is the force, the vertical force in the vertical Z direction in the body frame. And U2, 3, and 4 are the three torque values. So for the roll, pitch, and the yaw torque around the X, Y, and Z axes. So those are all our four separate virtual control inputs that we can apply on the platform. So what do we use those virtual control inputs for? So basically the idea behind those virtual control inputs U1 to U4 is that they give us an intuition on how we can fix tracking errors. So basically, as an example, if the attitude error around the x-axis is some small value, then we only need to apply some torque around the x-axis to fix this value. And this torque in that case around the x-axis would be represented by u2. So now, in order to get those virtual inputs based on the actual control inputs, which are the rotor speeds, we have this mapping from the squared rotor speeds to these virtual inputs. And this mapping is represented by the allocation matrix A. And we can basically compute this allocation matrix based on the geometry of the platform. So now we're looking at a control block diagram of the geometric controller. And we can see here on the left side, it starts with a position controller. The position controller based on the current position of the vehicle and a reference position. So here on the very left side, we see the reference position, velocity, acceleration, and yaw angle. So the small d stands for desired. Based on this difference between position and position desired, we compute a reference attitude, which is represented by this rotation matrix R, IB, desired. And this is then used by the attitude controller, which gives us the virtual inputs U2 to U4, which are then together with U1 fed into this control allocation that we saw in the previous slide, which then gives us, by the inversion of the allocation matrix, the rotor speeds omega 1 to omega n. And those rotor speeds are then eventually fed into the actual MAV, where they're executed by the propellers. So here we see the position control block, which is the leftmost block of the control block diagram that we saw in the previous slide. And what that does is that it computes the desired reference attitude, so RIB desired, based on some position error, some position and velocity error. So what we do is we take the current position and velocity error, and we use this in a PD controller to compute the Z vector of the desired rotation matrix RIB desired. And then once we have the Z vector, we can compute the remaining X and Y vectors. And those X and Y vectors only need to be orthogonal to Z. And otherwise, X and Y can be chosen freely based on a desired yaw that we can choose freely. And then once we have X, Y, and Z, we can, by that, directly construct the desired reference attitude R, IB desired, which is here on the bottom. So next we're going to look into how this reference attitude, RIB, is used by the attitude controller to compute the virtual inputs U2 to U4. In the lecture from last week, you already saw an attitude controller that was based on the Euler angle errors. So basically what you were doing there is that you linearized around the hover case and then designed a PD controller based on roll, pitch, and yaw errors. And this works for small angle errors, but it is definitely not globally stable. So what we're going to look at here now is the so-called geometric controller, which is valid for almost all possible attitudes. So this is the more widely and more correctly used attitude controller for multirotors. So in principle, the geometric attitude controller works quite similar to the attitude controller that you saw last week. So it's also a PD controller that works on an attitude error and an angular velocity error, but the attitude error here in this case is not computed by the Euler angles, but by this geometric expression that we see here. So it is a little bit more complex, but it is more accurate. So putting together the results from the position and the attitude blocks, we get those two equations for the vertical thrust, so U1, and for the torques, U2, U3, and U4. And we then use those four values in the allocation in the next slide to get the rotor speeds. Coming back again to the allocation, we now have computed the virtual control inputs U1 to U4, and we can now just take the allocation matrix A, take its inverse, and by that compute the rotor speeds omega 1 to omega n, like depending on how many rotors we have on our multirotor. So here again, an overview of the control block diagram as a recap. We start with a position controller, which gives us, based on a current position error, it gives us the desired reference attitude, RIV. This is then tracked by the attitude controller that gives us the reference torques, U2 to U4, and those are then together with the vertical thrust, U1, fed to the allocation, which then, by the inversion of the allocation matrix, gives us the rotor speeds omega 1 to omega n. So up until now, we just used the difference between a desired set point and a current state, scaled this with the PD controller, and then used this as an input. But so far, we didn't really care about the exact model of the multicopter or about any physical constraints of it. So as opposed to that, in MPC, we want the controller to be smarter. It should be able to predict the dynamics for all kinds of input and optimize the behavior that way. So how this works is that we have a simplified model of the system dynamics that is used to predict the vehicle behavior as a function of the control input. And then at each time step, we use an optimization problem that we solve to find the best possible control input that also respects physical constraints. And in the simple case of no constraints and linearized systems, this problem basically reduces to an LQR controller. And generally, this MPC solver could also be computationally quite demanding, depending on how accurately we define this. So here you can see again how this works. Suppose we are at time step k, then we use the system model to predict the dynamics up until time step k plus p, so within this prediction horizon, and then we optimize the inputs in this horizon to make the predicted output, which could be the pose of the vehicle, converge to the reference pose. And then basically we just repeat this optimization at each time step to make the pose converge to the desired pose. And here we see the mathematical formulation of the optimization problem. So we basically just minimize the integral over the time horizon from 0 to t, which is the end of this time horizon. And when we minimize the cost on the states, so x minus reference x, we minimize the input, so input minus reference input, and we minimize the cost on the terminal state, which is x of capital T. And this whole optimization problem is then subject to, first of all, the system dynamics, which is x dot equals f of x and u. And also u needs to be in the set u, which is the allowable inputs. For example, we can there constrain the rotor speeds. At the same time, x needs to be inside the feasible states, so we can there, for example, limit the velocity of the whole vehicle. And what we do here is basically that we minimize this total cost by varying u. So the result of this optimization is an optimal control input u that we then apply to the platform. So MPC can be used for complex and more aggressive control maneuvers that would not be possible with standard PD controllers. And this is mostly because the system dynamics are taken into account and also because the physical limits of the system are taken into account. So here in these two videos, we see on the top video how the multirotor is able to fly through those narrow spaces because it can pre-plan the necessary flight maneuver that allows it to be in this specific attitude while traversing through this sheet. And in the bottom video, we see how these two multirotors can avoid any collisions because both of them predict the flight path of the respectively others of the other multirotor in order to avoid any collisions. What's been coming up more recently is machine learning-based control. So here in the video, we see an example of reinforcement learning. So in that case, a neural network was trained in simulation and then deployed on the real platform for experiments. And the advantage of this is that we do not need any structured controller anymore. Like we do not need to separate position or attitude anymore, but instead we just give the position and attitude error directly as an input to the neural network, and what we get as an output are the actuator commands. So in that case, the rotor speeds. And we can see from the experiments that even in that case, the vehicle was able to still track the reference position correctly. So this was an overview of multirotors, their applications, and different control techniques. In the next part of the case study, you'll hear about how perception can be used for state estimation and for mapping of the environment.